A worker stands on the top step of a ladder, 10 feet above a concrete warehouse floor. He has just finished the final minutes of his 7th consecutive 12-hour shift. He loses his balance and falls. The ensuing investigation reveals a cascade of environmental failures. The ladder itself was damaged, incapable of providing a stable platform. The company had an inspection policy on paper, but no evidence the ladder was ever checked. Furthermore, no fall arrest or restraint systems were provided to the worker. Informed of the rising healthcare costs and impending lawsuits, the CEO's reaction is immediate and visceral. He demands management find out who is at fault and get rid of him. The company's safety director ignores that directive, relying on a rigid rule to bypass the assignment of blame. Search for facts, not for faults. Worker carelessness is rarely an isolated root cause. It operates as the final, visible link in a much longer chain of hidden system failures. To effectively prevent future catastrophes, engineers must completely abandon the human instinct for punishment and focus entirely on systemic deconstruction. To deconstruct an accident, we must first break down the chronological phases of a hazard using precise technical definitions. First is the unsafe condition, an environmental flaw like a rusted hook. Next is the unsafe act, workers walking beneath the suspended load. If the load drops but misses personnel, it is a near miss. An accident is when these exact events result in actual injury. The formal distinction between an incident, which includes near misses, and an accident relies entirely on the resulting damage rather than the mechanism of failure. The mechanics are identical, only the outcome changes. Minor accidents often generate superficial reports that only answer who, what, where, and when. Serious accidents demand rigorous analysis to extract the operational why. Breaking the chain at the unsafe condition or the near-miss stage is the only reliable method to keep the final accident from manifesting. True hazard mitigation requires a multidisciplinary avoidance matrix, stacking 4 distinct approaches to close operational gaps. This signage highlights the first pillar, the enforcement approach. It relies entirely on mandatory standards, strict rules, and severe penalties for non-compliance. This green signage demonstrates the second pillar, the psychological approach. This method pivots away from punishment to reward safe behaviors and encourage a ground-up safety culture. H.W. Heinrich's foundational industrial studies showed that 88% of accidents stem directly from unsafe acts. This data point is exactly why management teams lean so heavily on behavioral compliance. Apply these 2 behavioral pillars to our warehouse case study. A warning poster or the threat of termination will not correct the balance of a worker standing 10 feet in the air during hour 84 of their work week. Enforcement and psychology provide necessary baseline layers, but they are highly fragile. They rely entirely on human perfection holding up under edge case stress. The third pillar is the engineering approach. It seeks to design physical processes where worker carelessness cannot physically result in an accident. We visualize this through the 3 lines of defense hierarchy. You prioritize engineering controls first, administrative work practice controls second, and use personal protective equipment only as a final, thin layer of mitigation. The engineering approach operates on the general fail-safe principle. This dictates that if any individual component fails, the entire system must automatically default to a safe shutdown mode. It utilizes the principle of redundancy, ensuring that critical primary systems are continuously backed up by active standby units. Finally, it follows the principle of the worst case, requiring engineers to design tolerances based on the most extreme possible scenario rather than standard operating conditions. Returning to the ladder fall, an engineered solution, like a localized scaffold, isolates the human from the hazard. Alternatively, an automatic fall arrest system catches the exhausted worker in midair, saving them regardless of their unsafe act. The fourth pillar is the analytical approach, utilizing probabilistic modeling to dissect the exact mechanism of a hazard. Engineers rely on 2 primary analytical frameworks, FMEA and FTA. Failure modes and effects analysis, or FMEA, is an equipment-oriented bottom-up method. It traces how the failure of one small component ripples upward to break the entire system. Fault tree analysis, or FTA, is a top-down, event-oriented method. It starts with the disaster itself and works backward through the logic chain to locate the source. This fault tree analysis diagram maps out a strict Boolean architecture. It starts at a top-level event and branches downward through precise and/or logic gates. By tracing these pathways to the root cause, engineers bypass human blame entirely to reveal structural failures. To map the contributing factors of our ladder accident, we use an Ishikawa, or fishbone diagram. It categorizes variables feeding into a central problem. We populate it with facts: 12-hour shifts under people, the compromised ladder under equipment, and lack of oversight under management. The analytics definitively prove the CEO was wrong. Firing the worker is a superficial reaction that resolves 0 of the systemic variables identified on the board. Identifying an engineering root cause is a purely theoretical exercise if the company refuses to pay for the engineered solution. The final analytical tool is the cost-benefit analysis, utilized to translate engineering necessities into financial terms that management understands. We calculate the annualized cost of implementing a new engineering control by combining capital depreciation, say a $4,000 initial cost amortized over 8 years, with an $800 loss in production speed. This produces an expected annual cost of $1,842. Then we calculate the financial benefit. We establish the tangible and intangible costs of an injury at $2,750 and multiply that by a projected reduction of 1.1 incidents per year. That yields an expected annual savings of $3,025. Comparing the hard costs against the preventative benefits reveals the exact return on investment for the safety intervention. Even when stripping away morality, rigorous safety engineering is a mathematically profitable investment compared to the crushing expenses of post-accident litigation and operational downtime. The conflict at the center of the warehouse fall is a matter of priority. The enforcement approach demands a scapegoat, but the analytical approach demands a solution. Integrating administrative rules, behavioral psychology, fail-safe engineering, and Boolean analytics creates a fault-tolerant safety matrix. To actually protect a workforce, management must actively suppress the human instinct to assign blame. Robust systems do not rely on human perfection. They anticipate human error, deploying engineering to ensure that when people inevitably fail, the system catches them.